So my name is Rutkowska. I work for Kernel in Advanced Marvel Labs, and my talk is about subverting Vista kernel for fun and profit. This presentation is based on the research done exclusively for Kernel, and it was first presented 2 weeks ago on a Cisco conference in Singapore. It consists of 2 parts. First part is how to bypass Windows integrity checking for loading kernel drivers into kernel. And the second part is about creating malware which is based on hardware virtualization technology from AMD. Okay, so part 1. So in Vista 64-bit, for the first time, the new policy has been implemented to disallow even administrator to load unsigned drivers into kernel. This was explained as a step towards fighting kernel malware. And for the first time, it was implemented in Beta 2, build 5384. So as for today, officially, it's not possible, even for administrator, to load any unsigned driver into kernel. This mechanism can be deactivated by 2 legal ways, which were provided for testing. So one way is when user attaches kernel debugger during when system boots, and the other one is when user presses F8 when system boots. So this is for testing. There's yet another way to disable this mechanism, but this is only available in beta version. It will not be available in a production version, and this is by editing startup options using BCD edit. Okay, so now we will think about how to bypass this mechanism. First, we should observe that Vista allows, like any other Windows operating system, like XP or 2000, for a user mode application to get access to routed sectors. This is completely legal and documented way. You can read about it in SDK, and just enough to use create file with the arguments you see on the slides. So, like this one, you get access to logical device, and this one, you get access to physical device. I hope you can see the cursor. No? Yeah. Okay. So this allows us to read, well, among other things, to read and write to page file. Page file is something which is used by kernel to page physical memory, which is actually not used to free physical memory for other applications, right? So the code is page to page file. So we have the ability to modify contents of page file by just accessing routed sectors. And this page file may, it not necessarily does, it just does contain, it may contain code and data from kernel, page from kernel. This sounds very easy, but there are some challenges here. First challenge is how to make sure that the interesting code sections or data sections will actually be paged out into this page file. This is the first challenge. The other challenge is how to find that code which we forced to page out, somehow forced to have paged out, how to make that this code, how to find that code inside page file, which format is unknown for us. Another challenge is how to cause that this code, which we are going to modify, which is in page file, how to cause this code to be loaded into kernel again, and how to make that it will be executed again. And I'm going to tell you how to solve those challenges. Yeah. The first challenge is how to make sure that we actually force kernel to page out into page file interesting code sections. So the easy way for doing this is to just call standard allocating routine like virtual alloc, which again is perfectly documented function in SDK. So when the systems, when some application, some user mode application starts allocating more and more virtual memory, the system will try to back up this memory with physical memory. And as we will see in the next slide here. I hope you have the copy of slides on your notebook so you can see the slide in a better way than here. But it shows that Okay, this was taken on a test system which had 1 gigabyte of physical memory. I used standard performance monitor to take this picture. So first we have around 1 gigabyte of physical memory available. Then we start allocating memory. In this example, I allocated 500 megabytes of memory. So I asked for 500 of virtual memory, but the system had lots of physical memory left, so it actually backed up all the memory with physical memory. So we noticed that the amount of physical memory dropped down to 500, 600 or whatever. So then was another allocation, second allocation. So the system we're trying to, again, allocate as much physical memory for my virtual memory as possible. And you can see this green line here, and this green line here is the amount of available, the amount of code, the amount of bytes of code of drivers, of kernel drivers, which are in physical memory, right? So number of resident pages, probably pages of kernel drivers. So we see that at the beginning, and by the way, it's a different scale. So the red graph is like 1 gigabyte here, and the green line, this is around 4 megabytes. So there are two different scales. And we see that at some point, when there was not enough physical memory for those allocations made by user mode application, system started paging out kernel code drivers, kernel mode drivers to page file, which we can observe by this green line dropping down here. And by repeating those allocations again, which were made by user mode application, we see that kernel was paging out more and more kernel code drivers until at some point, some like critical point where no more memory from kernel were paged out to page file, and which resulted that subsequent virtual alloc calls were not backed up by physical memory. But this is not a problem for us. The interesting thing is that we can, by issuing a lot of virtual alloc, by calling virtual alloc function for many times, we can make lots of, like we can see, many megabytes of kernel drivers to be paged out. And of course, the question is which drivers or which pageable sections of which drivers will be paged first. Of course, those which are unused, right, are very rarely used. And what could be paged as far as kernel mode is concerned? So first we can have all the pageable sections of kernel mode drivers that can be paged, and the pageable sections are recognized by the fact that the first 4 letters of their names is page. And also we can have data which were allocated from page spool. They can also be paged out to page file. So now we need to find a target which would be a very rarely used driver, which would contain pageable code section, and that code section would contain some function which would be possible for this function to be called from user mode. And I just found one of those one example of a driver like this. It's null.sys. We can have a quick look at in disassembler in this driver, and we will see that it does contain one pageable section. And actually, this pageable section contains driver's dispatch routine, which is very good news for us because driver's dispatch routine can be very easily called from user mode by just issuing create file for the object created by this driver. So we have it's not done, but we believe we have a way to force some of the drivers to be paged out. Now how to find a interesting code in page file. This is easy because we can just do a pattern search. Because if we consider, what we would like to do is we would like to override the first few bytes or few dozens of bytes of the original function of the driver with our shellcode, right? So we can just find this beginning of this function by pattern searching. If we take like the first 64 bytes of the function, there's very, very little probability. In fact, I never experienced like to find something else in a page file. Even though page file can have like many gigabytes, if we search for 64-byte string of opcodes, it's very, very little probability that we find something else than our function. So actually, I already mentioned this. Because in this exemplary driver, null.sys, the function which actually sits in this pageable code section is actually dispatch routine. So it's very easy to make sure it will be called. And automatically, if we can make sure that this function will be called, it means that it will be first loaded from page file. So by modifying this function, so first we make this function to be paged to the page file, we modify it, we override the first bytes with our shellcode, and then we issue create file call for one of the objects created by null.sys, and this automatically causes that kernel will first load that page section, those paged section into kernel and execute it. This is all we need. So we allocate lots of memory to cause unused drivers to be to cause code to be paged. We replace this paged out code with some shellcode, and we ask kernel to call the driver dispatch routine. And this was actually implemented as a one-click program. A special heuristic has been used for actually, because one of the problems is how much memory do we need to allocate so that our null.sys code will be paged out. We cannot actually check, like we cannot check from user mode whether any given code section of any given kernel driver has been paged out or not. So we need to find out a good heuristic for doing that. And this heuristic is based on this graph. We're just trying to find out when this green line becomes flat. So this was implemented as a tool. And the shellcode used in this demo, which was written by Edgar Barbosa, is very simple. It just disables kernel signature check. There's a global variable in kernel which is of course set by those F8 or attaching kernel debugger, which says whether we should do integrity checking or not. So we just put 0 to this variable, which allows for any subsequent unsigned driver to be loaded. Of course, we can imagine many more advanced shellcodes to be used. The sky is the limit here. Okay, the demo. Oh, it's not that one. Sorry. We have a Vista Beta 2. We try to load debug view standard tool from sysinternals, which is not signed, of course, and we get a message error loading debug view driver because it's not signed. I guess in a few months it will be signed, right? So now we start kernel strike attack. We see allocating lots of memory. Allocating. Memory was allocated, and now we were opening routed sector. We were parsing NTFS file system to find out which sectors correspond to page file. Then we are searching those sectors, and we override the first 24 bytes of the function with our shellcode. It took 23 bytes to come up with this very simple shellcode, which overrides this global variable. And we try to load debug view again, and we get it working. Question?
I think that's one more challenge.
Say it again.
I think that's one more challenge. How do you make sure when you are modifying the page file it's not getting changed by the operating system?
There's no reason for operating system to change paged out code of the driver, right?
But maybe at the same time the operating system is loading some driver and to get something else where to page file. operating system.
It doesn't matter if it allows something else from page file. We only, okay, the question was what happens when the operating system changes page file at the same time when we are trying to modify it, because we modify page file by raw disk access and operating system access page file by some other means. But it doesn't matter because we modify only one physical sector of the disk, so we don't care what happens on the other disk sectors. And there is like very, very, very little probability, almost zero, that the system would like to modify the page, the disk sector which contains the code of this very dispatch driver function which I'm modifying, because there is no reason for the operating system to modify the paged code section, right? Okay. Maybe I will just finish this first part. We'll have like 2 minutes for questions, and then we go to the second part, okay? Because I would like to tell about possible solutions to this problem right now. I see 3 solutions to this problem. Solution number 1, forbid raw disk access for user mode applications, right? So that create file bracket / dot / c colon will not work anymore. Of course, this will break compatibility because, well, as I said, this is a documented way. It's described in a SDK. So it's not a good way. Of course, it will break probably many applications like disk editors and deleters, some probably antivirus programs, some databases maybe. And if Microsoft did this, then I could imagine that creators of those applications like disk editors or whatever would come up with their own kernel mod drivers for allowing access to those raw disk sectors, which would read, and of course those drivers would have to be signed, right? So then it would be nothing which would stop attackers from just copying those drivers and using them just like disk editor is using them, right? It just would be necessary to reverse engineer the interface between user mod application and their custom kernel mod driver. So this is very, very bad solution. I don't recommend it. Solution number 2 is to encrypt page file. Once we get the page file encrypted, it wouldn't be possible for the application to find and modify in an interesting way the kernel code which is there. There might be some, well, I expect a big performance impact if this was implemented. And actually, I just yesterday talked to some Microsoft person, and he told me that it is actually possible to turn on page file encrypting in Vista. I think it was introduced in Vista Beta 1 or something like this. So there's a registry key which says enable page file encryption, and this is used, of course, for not for preventing this kind of attack. This is used for this encrypting Diskkeeper or whatever, Bitdefender. I don't know what the performance impact is of this, and I believe it encrypts all the page files. So not only kernel code which is paged, but also user mod code. So I would expect a big performance impact of this. Solution number 3 is to disable kernel mode paging, because today we have lots of memory, lots of physical memory, and the amount of all the memory which is pageable in kernel code is around like 70 megabytes. So when we have like 1 gigabyte or like 4 gigabytes of memory, those 70 bytes is really it's just nothing, right? So personally, I would recommend just to disable paging of kernel code and data, right? So this pageable pool should become non-pageable pool. And again, you can actually manually disable kernel code paging in registry. And yeah, that's what I'm doing for my home machine. Just because I have 4 gigabytes, so it doesn't really make any sense to have paging enabled. But it's quite interesting to notice that those 2 solutions, like to enable encryption of the page file and to disable paging, they still allow for bypassing this Microsoft policy because Microsoft said in their paper about driver signing that it shouldn't be possible to turn off this mechanism permanently. Only two ways are allowed: pressing F8 every time the system boots, or attaching kernel debugger every time the system boots. But even if we had a smart user who disabled paging, we still can enable it, reboot the system, and then it's gone, right, forever. So, of course, it's not that cool as this attack I just showed, which doesn't require reboot, but it's still something which bypasses Microsoft policy. So, in my opinion, this should be hard-coded, right? Just disable paging forever. Okay, so this is the first part. So the present attack doesn't rely on any implementation bug. It also doesn't require any undocumented functionality. Create file is perfectly documented thing. I think Microsoft did a good job with this mechanism. It's a little step forward into securing kernel. It's just, it's just very. It doesn't mean that Vista is so unsecure. It just means that it's just not that easy to turn the generic operating system into a very secure one. Okay, so just before we go to the part 2, some questions. Okay, yeah. Say it again. Uh-huh.
Page file. Great. So the page file can only be accessed by the system instead of by user mode. Wouldn't that prevent you from being able to read the page file from a user mode program?
No, but you cannot prevent it, because if you allow raw disk sector access, because the ACL on raw disk access is to allow administrator to read it.
Yes, you're correct.
Yeah. Okay. Okay. About UAC, yeah. All right. The question was how I got around the user account control. Well, I just pressed accept. The command prompt, yeah. This. I'm not bypassing UAC, okay? So on the demo, I just opened this console as the I said run as administrator and just press accept. Bypassing UAC is another thing, and UAC is another good step towards securing kernel. But from my experience is that all the Vista users are complaining about UAC because it pops up every 5 minutes and they automatically press accept, right? So I would expect that if somebody downloads some malware or gets it as an attachment, and after running it, it will display this constant dialog box, most of them will just press it. But bypassing user account control is another thing which is interesting and is not covered here. Last question for this, okay?
What about encryption of the volume with the BitLocker?
I haven't checked it, but as far as I understand this technology, it is to prevent somebody others who steal our laptop or whatever to read it. It's not to prevent administrator from reading his files, right? Because yeah, but I know the key, right? The decryption key as administrator. So I would expect that this encryption, which is here, because if there was, I would expect that this encryption, which I told about using this with the solution number 2, this is what can stop it, because the key is kept in kernel. Why this keeper is about what's the name? Bitdefender. BitLocker, oh yeah. BitLocker is about preventing others and not administrator from reading it. But I haven't tested.
Okay. I don't know, in fact, if the administrator has any simple means of accessing the key BitLocker is using to encrypt the volume, so I don't know the answer either.
Okay, so somebody needs to test it. Okay, I think we will go to part number 2. Okay, one more question. From user mode. No, as I said, you need to have administrator access for this. Can you say that again?
So if you call create file from any user mode program, null.sys gets loaded into the kernel back from the page file?
If you call create file from any process which has administrator rights, it can get access to route sectors.
Oh, so you're using create file to write to those sectors, right? To write the data.
Create file returns handle, and then I use write file.
Right. So, but what are you using to make sure that the modified code from the page file gets loaded back into memory?
To modify what?
After you modify the page file, how do you make sure that that code is actually executed?
Oh, as I said, because I call, well, create file is used for two things here.
Okay.
First thing is to create file is to first to get access to routed sectors to find those
Sure.
bytes in page file, and the other way, the other thing is that create file is used to open device object created by this kernel driver, which I am exploiting. And this actually makes kernel to call this code.
Thank you.
Okay, one more question.
In your testing scenario you showed us, do you have page file on the system volume? Because I don't believe it's possible to open the raw disk for write. You have to locate it.
No, you don't have to. You can open. No, it was normal. It was standard installation of Vista. Nothing was disabled or enabled, especially. Because the question was, how was it possible to get access to page file, although it was opened by kernel, right? So with this no share flag, but we bypass it because we are accessing routed sectors. So as you've seen on this presentation, I was opening master boot record, and I was parsing NTFS information to find out which sectors contain this page file actually. So I was not opening pagefile.sys. I was opening routed sectors. Okay. So let's go to part number 2, which is about abusing SVM technology for creating undetectable malware. What we have today in rootkit field is that we have something I call invisibility by obscurity. For example, FU, like Jamie Butler, works by unlinking, or Futu, by unlinking some kernel objects from some kernel lists, which makes them unavailable for kernel. But once we know the algorithm, once we know the concept of the rootkit, we can always write a detector. Sometimes we have some problems with reliability of those detectors for some obscure reasons, for some different reasons. But usually, theoretically, it is once we know the concept, it's trivial to write a detector. So, for example, DeepDoor, the rootkit that I presented half a year ago, modified some NDIS data structures, some function pointers inside data structures, but again, it was completely undetectable over that time. But again, once we know the concept, once we know which pointers are modified, we can detect it. And also, I believe that there is only finite number of ways how we can actually implement any given malware. Like if we consider network backdoor, there probably will be like 3 dozens of ways how we can do this, like hijacking NDIS code, hijacking NDIS pointers in many different ways, like we've seen in Alexander's presentation. We can do this in really, really different ways, but not infinite ways, not infinite number of ways. But anyway, once we know the concept, we can detect it, which is so boring. So now imagine a malware which doesn't rely on a concept to remain undetected, which cannot be detected even though its algorithm is known. So how it works? So it's made publicly available, and we can go even a step further and imagine malware which would be undetectable even if its code is made public. This is something which reminds me of a modern crypto. We know the crypto algorithms, but we cannot decrypt the message, right? The idea behind Blue Pill is to exploit SVM extensions of AMD. Actually, the idea is very similar to what Dino presented just a few hours ago, but he did it on Intel VT, and I did it on SVM. So the idea is to provide very thin hypervisor, which will control the OS, and hypervisor will be responsible for intercepting any interesting events. And which events will be interesting depends what actually we want to implement. Keylogger, kernel backdoor, whatever. SVM, Secure Virtual Machine Technology, also known as Pacifica, it was introduced on May 23rd. No, it was not. It was released. So the first processors were available on the market, at least theoretically, on May 23rd. I managed to buy them during the first week of June in Poland, so they were probably available much earlier somewhere else. And the processors which support SVM are all the AM2 socket processors. And these are the only AMD processors which support SVM. Okay, so this AM2 hardware is available, but for example, I didn't manage to find any laptop with SVM technology, which results that I will not be able to show live demo of Bluepill, which is a pity because I'll tell you later why. I'll just show you a demo movie. So SVM is a set of instructions which can be used to implement virtual machines on AMD 64. And there's a MSR register which is called EFER, which is for many different things, but it has bit number 12, and this bit, when set to 1, enables SVM mode. It doesn't mean that once we enable this bit, we are becoming hypervisor. It just means that the SVM instructions are available for the processor. And you can find detailed reference in Architecture Programmers Manual, Volume 2. Okay, so this is how SVM works. This is the official explanation of SVM. Can you see the cursor? Yeah? So first we have SVM disabled, so there is no notion of host or guest, but still we are the native machine here, right? We are executing some instructions. And then we decide to create a virtual machine. So first we create something which is called VMCB, Virtual Machine Control Block, which consists of two parts. One part is the state of the guest, and the other part is the control block. And the state contains information like RIP register, RSP register, segment registers, and all the other state which would be necessary to create virtual machine. And control block contains information about what kind of events you would like to intercept. For example, that you would like to intercept every call of SIDT instruction, or every debug exception, or every page fault exception, or whatever. There's a list of few dozens of events which we can intercept. So once we create this VMCB, once we fill it with our preferred values, we can call VM-run instruction. This is one assembler instruction. This instruction takes an implicit argument, which is the address of VMCB. And this instruction is similar to call, because it starts the execution of virtual machine, which now executes, just like it was a function, it executes until some event occurs, event which we would like to intercept. So let's say we wanted to intercept, I don't know, page fault exceptions. So the operating system here executes until a page fault exception occurs, for example, or debug exception occurs, or somebody issued SIDT instruction, whatever, and then we break into hypervisor and we continue execution from the next instruction after VM-run, just like if it was a call instruction, a generalized call instruction. And we call, from this on, we call this hypervisor and we call this guest. Okay, I think this should be obvious. And this is how Pacifica works, and this is how Intel VT VTX works. And now we have the slides, which is the most important slide during this presentation. This is how Bluepill works. So again, we start here. This is our native operating system. Let's say it's Vista. So it is doing many different things, and suddenly it loads our Bluepill code. And this Bluepill code at some point, well, let's say call a Bluepill function. And this function does the following. It first enables SVM mode by setting this bit number 12, then prepares VMCB in a very tricky way. The tricky way is that we need to prepare things in such a way that this created VMCB, this created VM, this created virtual machine would be the same as the current operating system. So we try to clone our operating system into VM. So it requires some tricks. One of the tricks is that we make RIP. RIP is the 64-bit version of EIP register. We make it to point to the return instruction from this function. And then we call vmrun. Vmrun creates virtual machine, and it starts executing from this address. So it starts executing from return. So it starts executing from here. So suddenly, we were here, we were the native operating system, we called this Bluepill function, and we landed here, but we are now inside a virtual machine. And we continue executing. Let's say we have here like driver entry for our Bluepill, and here we like have return status successful, and the operating system is doing something else, right? Switching to other processes, whatever. But now it executes inside virtual machine. And this here is the hypervisor, because we executed this instruction and we execute here. And let's say we wanted to have a keylogger. So we said that we want to intercept every interrupt. I don't remember what's the interrupt. Some keyboard interrupt. So it executes. Suddenly user presses key, and we have this intercept, and we land here. And here we have a big switch to see what event occurred. We do the appropriate action depending on the implementation, and we execute vmrun again, and we continue our operating system. So this is funny to notice that on this slide we had native operating system, which then became we had this native operating system, which then became hypervisor, and we had guest here. But here we have native operating system, which became guest, and we had something which wanted to become guest, but became a hypervisor, actually. And the funny thing is that this operating system doesn't know that it actually became guest. This all happens on the fly. So we don't need to modify any boot sector. We don't need to take control before the operating system boots. This is very important because this means that we can create non-persistent malware with this, which means that we cannot be detected by cross-view detection, like offline analysis or anything like that, because we don't modify disk. It's not necessary. Of course, the problem with non-persistent malware is that it disappears after a system is restarted. But there are several things which should be considered here. First of all, if you consider servers, they are very rarely restarted, so this is not an issue. If we look at the Vista, the power off button actually doesn't shut down the system; it only puts it into suspended mode. And also, we've seen this Subvert rootkit, which I'm going to talk about in a minute, from Microsoft Research, which used VMware, and they actually implemented emulated shutdown and emulated restart. So we probably can do the same. I don't know, I haven't implemented yet, but we can probably do the same. So we might just get rid of, we can actually emulate all the restarts, so we can have actually our non-persistent malware to become persistent without any modifications to disk. This is something for the future. Okay, Subvert rootkit was released a few months ago by Microsoft Research and University of Michigan. It uses a commercial VMM, either virtual PC or VMware, to run original OS inside VM. And it's necessary to compare those two creations. So Subvert is on the left and Bluepill is on the right. Subvert is permanent. It needs to be permanent because it must take control before the original operating system. Bluepill is not persistent. It works on the fly, so no modifications are necessary to disk sectors. Second, Subvert was created for standard x86 architecture. It only uses software virtualization as implemented in VMware or virtual PC. That means that it's not resistant against SXDT attacks. Like, for example, I implemented a little program called Redpill a few years ago, which can be used to detect virtual machine by just using a design issue with this. Because x86 architecture doesn't allow for full virtualization, because there are sensitive instructions which are not privileged. On the other hand, BP relies on hardware virtualization, which promises full virtualization. So Redpill-like attack shouldn't be possible to detect Bluepill. Subvert is based on a commercial VMM which creates virtual hardware. So once you run VMware, you have this VMware network card, VMware graphics card, and etc., which of course allows for very easy detection. Bluepill uses very thin hypervisor, which doesn't intercept any I/O communication, which means that the Bluepill operating system actually uses the same hardware as the original one. There's no difference in hardware. I'm gonna show it in the demo. So what happens when you install Bluepill inside a system which was already Bluepilled? So this is a question about nested virtualization. As Dino said today, if we didn't handle this nested virtualization correctly, then it would allow for very easy detection by just trying to create a test virtual machine. And if it fails, then something is wrong. Of course, the easy way for cheating is just to intercept CPU ID, just like Dino said, and just pretend to the operating system that this processor doesn't implement SVM, but again, this is very easily detectable by a user who is aware that actually she bought SVM capable processor. So we need to handle nested VMs. So here we have hypervisor. So this is Bluepill, right? So Bluepill called vmrun to actually run the operating system, the native operating system, which was Bluepill. So this is our operating system. This is Bluepill hypervisor. So let's say that this Bluepill operating system now tries to create virtual machine by itself. So it calls vmrun. And of course, so first it creates VMCB, let's say called VMCB number 2, because this was VMCB number 1. So it first creates VMCB number 2, but instead of creating virtual machine, we are going back to hypervisor, because hypervisor intercepts any vmrun calls. Vmrun is another example of events which can be intercepted. We can intercept any vmrun calls. So we are going back to our hypervisor. And now we realize that this was vmrun called from our guest. So we call vmrun on behalf of this guest by using VMCB2 prepared by this guest. We can actually access this, and we create virtual machine for this guest, which runs. So it's running until some event occurs, the event which this guest said that it would like to intercept. So let's say, I don't know, some interrupt, whatever. So of course we are going back to our hypervisor, not to this hypervisor, but we are realizing that it was intercept from VM number 2. So we resume our operating system just after this instruction. So the operating system thinks that that this happened just here, right? That's only a time difference. So the operating system thinks that actually it is a hypervisor, but in fact it's not. Another detection is, of course, by timing analysis. For example, we can assume that but this is not a lipstick, it's just a moisturizer. Because people then say, why do you use lipstick during your talks? It's just a moisturizer. So we can assume that some instructions will always be intercepted. One example of such instruction is read MSR. Just because to enable SVM mode, we need to set this bit number 12 to 1. So if we didn't intercept read MSR for the EFER register, then it would be trivial for the guest to notice that this bit is set to 1, which is suspicious, right? So we always can assume that read MSR is intercepted. So not surprisingly, the time needed to execute read MSR inside VM takes more time than on a native operating system. So, well, that sounds obvious, but the first problem for the detector is that detector should have some baseline to compare with. So we need to know how much time read MSR, how much time it's necessary for read MSR to execute on a native operating system, and how much time it's needed to execute it inside VM. Like we've seen on the Dina's presentation that it took like 200 cycles for the native operating system and 3,000 on a inside virtual machine. But if you wanted, but we knew that first it was not virtual machine, and then we knew that it was virtual machine. So we had some baseline to compare with. If we consider that there are many different processor models, it's not so obvious that by just seeing some result like 500, we don't know. Maybe it's optimized processor, and this 500 is maybe inside VM, or maybe it's a slower version of some processor, and 500 is just a normal latency for this instruction. But even if it was constant, even if we had this baseline, even if we could look into the optimization guide, which has a table of the latencies of the instructions, and even if it worked, then there's an easy way for us to cheat about cycles. It's easy for us to cheat about the time for the guest. So again, here we have hypervisor. It calls VM run, so we're executing inside virtual machine. And let's say we call read MSR here. So this is intercepted. We go into hypervisor. Hypervisor does do something to service this call, and then it restores the execution of guest. So it took like Tx extra time, extra cycles. So we can use, there's a special field called TSC offset inside VMCB in this control block, which is the offset which should be added to guest timestamp counter before it's resumed. So we just add minus -x here. So if guest called read TSC instruction, which is used for reading timestamp counter, and read another and remember the result, and then it called it again here, so it will not notice this extra time, right? Just because we subtract this time which we added. So the only reliable way for getting time on a machine is to use external timer. And one of the examples of external timers is NTP, Network Time Protocol. But again, Network Time Protocol can be, like, the packets can be intercepted by hypervisor. So we need to use either some kind of like VPN over SSL or some NTP over SSL or VPN, or we need to use some custom NTP-like protocol, which I don't think is very practical. And also we have another problem with this, because when we used read TSC for time profiling, it returns the number of cycles, while when we are using NTP, it only returns the number of milliseconds. I don't know the accuracy of NTP, but it's around milliseconds. So this is not very good, and we cannot use it for actually adjusting our clock, because our clock can be cheated. So we need to rely only on packets we get. So I don't believe, and I stress the word believe because I might be wrong, that this might be used for effective detection. But we'll probably work on this, so maybe you should expect a talk how to detect blue pill within the next few months. Okay, this is what I said. So blue pill is just a way for silently moving the running operating system into a virtual machine, hijacking operating system and inserting our own thin hypervisor. It can be exploited in many various ways, not necessarily malicious, but malicious are one of them, of course. And one example, very simple example. I didn't have time to develop anything more complicated. This is a network backdoor, something very similar to DeepDoor, which I presented in January, but this time implemented with the help of this blue pill technology. So we use two debug registers to hijack execution of those two functions, receive net buffer list and send net buffer list from NDIS. And blue pill intercepts debug exception. So once those functions are going to be executed, debug exception is raised, it's serviced by blue pill, and the execution is returned to guest, but guest doesn't even realize that the debug exception was raised because hypervisor can decide if it should pass the exception to the guest or not, or just service it by itself. So we are servicing the debug exception by ourselves, so guests don't even realize that debug exception was raised. And of course, blue pill takes care about protecting those two debug registers, so that if the guest tries to write to those debug registers and then reads, they will behave like if they were not used, right? So they are emulated for the guest. So not even a single byte is modified inside NDIS data structures, nor NDIS code, nor any code or data of kernel. So there's like here we have blue pill code, and here we have kernel, data, code, and there's no modifications introduced by this code. This code is just standalone, sitting somewhere here. So like we seen Alex's presentation just an hour ago, and he was talking about, oh, this method is very stealthy because it requires only one double word modification inside the system. This method requires zero double word modifications. And of course, delusion, as every good network backdoor, comes with own private TCP/IP stack, which is based on lightweight IP, which is a popular stack used for microcontrollers. And now this is how the demo looks. This is the scenario, right? So we have a computer which will be blue-pilled, and we have a attacker computer which will connect to this delusion backdoor. And delusion is created in such a way that it observes incoming traffic to all TCP or UDP ports, and once the magic packet is sent to one of the ports, whatever, open or closed, it's not important. So if the packet is magic, then delusion hijacks this packet and serves the packet and send reply. And also another computer should be used for debugging blue pill over serial connection. And in this demo, this computer and this computer will be one computer. So you will see a serial console for debugging and command prompt and netcat for sending those packets to delusion backdoor. Okay, demo. So I really wanted to show you a live demo because it's cool to see how you can actually play 3D chess on Vista when it's blue-pilled, because it still can use all your 3D graphics card features, but I couldn't show it on this demo because the program which I use for capturing were able to capture only 1 frame per second, which is not very good. So we have Vista Beta 2, which is not compromised yet. We see the hardware. We have Western Digital, NVIDIA, Lighton. We have Realtek for network card, AMD Athlon, something. You see that I first ran kernel strike to get access to disable kernel snatch checking, and now I just loaded delusion, right? So the system got blue-pilled. And this is the output from the delusion. So you see that EF-ER register was set to enable SVM, so this 4 becomes 5. And yeah, we are inside matrix. So we are going back to the machine which was just blue-pilled. As you saw, just like in Dino presentation, nothing happened. It just becomes blue-pilled and without any screen blink or whatever. So I'm scanning for hardware again, just to show you that the same hardware is available. We have Western Digital disk, NVIDIA graphics card, we have Realtek network card, and the same processor and whatever. So then we will check the IP address of this computer. And this is 192.168.1.206. So we are going back to the remote machine. And we will try to connect to this. Oh, this IP address is 1.10. So we will just send a magic packet just to show you that the kernel network backdoor actually works, so that those functions are hijacked. So we are sending magic UDP packet with string password with 0, written with 0. Yeah, we get information that the magic packet got received. I'll just show you that we can connect to this backdoor. So we are connecting using source port 10 to port 445. This could be whatever else. Source port number 10 is just a way of, it's just a magic port, right? So this is how magic packets are recognized. Magic port plus magic source IP. But I also can show you that the SMB protocol still works by connecting to this machine, so file sharing still works, although it uses 445. So it doesn't interfere with the standard operating system functionality. And one more thing I would like to show you is something special. So once we allow it to run for a few minutes, we get this funny message. Somebody tried to read EF-ER register from the guest. And the question is, do you have any idea who tried, what kind of application, what kind of process tried to read this EF-ER register? An idea? What? No. No, it was PatchGuard. It was PatchGuard. PatchGuard is this famous kernel production by Microsoft introduced for 64-bit operating systems, and every few minutes, like every 5 minutes or something, it verifies the it verifies the integrity of some code sections like ndis.sys code section, ntus-kernel.exe code section, integrity of IDT table, SDT table, and among other things, integrity of some MSR registers, like, for example, integrity of EF-ER register. So if we didn't intercept EF-ER, if we didn't intercept read MSR, PatchGuard would catch us. But of course, it's a generic technique. We don't care about patch guard. It's just that we bypass patch guard automatically, right? By just ensuring that guests cannot recognize that it is blue pilled. So we get we get patch guard bypassing for free. One interesting thing to notice is that if we left this operating system for a few hours, we can see lots of calls from patch guard. And the funny thing is that those calls originate from random addresses. So patch guard from time to time is moving in memory, right? So to make it difficult for Metasploit guys to disable it. Okay, I distinguish between, well, I distinguish between two levels of stealth for blue pill. Something I call blue pill level 1 is something which should be undetectable even though the concept is known. So I just made the concept known, and still I believe it wouldn't be possible to create any practical detector for this kind of thing. But of course, because okay, so this is level 1. But now we have level 2, which should be undetectable even if I made the binary code public. So this would be about avoiding signature-based detection. Blue pill level 1 is everything we need for a targeted attack. Just because blue pill does not, or blue pill-based malware does not introduce any modification inside kernel. So, and if we don't know the code, we cannot just detect it, right? Because we cannot use any kind of technique, like standard technique to see if something is hooked or not, and which would lead us to the code. It's just something which might look like a picture or whatever. There's no connection between kernel and this blue pill code. So blue pill level 1 is something which should be enough, more than enough in any targeted attack. And this is what I implemented. Blue pill level 2 is the future, has not been implemented yet, just because to implement it correctly, we need two more mechanisms. One of them is nested pages, which is going to be introduced by AMD somewhere in 2007, as I heard somewhere. And another one is IOMMU, which I heard that it is also going to be introduced somewhere in 2007. But blue pill level 2 is something interesting from theoretical point of view, and blue pill level 1 is just because we can generate blue pill level 1 code in many different ways, like we can use a polymorphic compiler for this. This is something which is the real threat right now. Like I would never consider, if I was an attacker, I would never consider using blue pill level 2 just because it would be too complicated and just doesn't offer any more features over blue pill level 1, instead of, well, despite the fact when we use it in a massive attack. Okay, so generic blue pill detection. I just thought about this timing analysis, and then we can cheat about it by using this TSC offset field. And I said that the only practical way would be to use NTP or other NTP-like system, but it seems problematic to me. So you can ask if it's possible, maybe, to create something like red pill, but this time for this Pacifica technology. It might be possible. It might be like Pacifica might be buggy. I say buggy in apostrophes just because AMD documentation doesn't really say that they offer 100% virtualization. They only talk about secure virtual machine. But still, everybody believes that hardware virtualization can be used for for full virtualization. And if we had a way to create program which would behave differently inside VM and outside VM, this would mean that actually we don't have a full virtualization, right? So So I would call it a bug in this SVM technology. But I stress this, that this is bug in apostrophes because it doesn't necessarily mean that the security can be subverted. It only means that it's not really 100%. Well, it's not really a 100% virtualization in this case. But of course, I'm not aware of any way how to create red pill for SVM. Although I heard from a trusted source that there are some bugs, implementation bugs there, but it's just a gossip. We also researched together with Alex Tereshkin some theoretical ways how to detect blue pill level 1, which are not based on timing analysis. And it seems that the only one way would be a very smart brute force attack, which would allow for crashing the system when it is blue pilled. So we run the detector, and we say to the user, watch for the system. If you see a blue screen, then it means that you had a blue pill, right? Of course, it's something which. Well, this is something which sounds very unpractical for me, but this is a theoretical way to detect it. We haven't implemented it yet, but we'll probably do this. It's a brute force attack. Well, but still. Well, patchguard is not really detector. Patchguard is something which is intended to discourage vendors for creating applications in a inelegant way, right? Yeah, but it's not meant to be a detector. It's meant to force the independent software vendors, like personal firewalls developers, not to use tricks which they shouldn't use. Because if they use it, then they would notice that the system crashes every 5 minutes, right? So it's not really for the user. It's not really for use by corporations to detect the integrity of their networks. It's for discouraging independent software vendors from using forbidden techniques, which they shouldn't use. And by the way, I think that patchguard is actually a very good thing, because like I spent many years on writing different rootkit detectors, and one of the biggest problem I had was to distinguish between some personal firewalls and rootkits in a generic way. And I think it was in the first talk today by Jamie Butler, it was mentioned that sometimes it's virtually impossible to distinguish if it's personal firewall or rootkit, just because the same hooking technique is used. So this is crazy, right? So I really support Microsoft with this idea of patchguard, because we should really get rid of this. We should really, make our operating system more elegant. Because now, like SVV, which I released a year ago, suffered from so many false positives just because of this reason. So currently, the only good way for detecting rootkits is something which combines generic detection with signature-based detection. And of course, I hate signature-based detection because this is so bad idea, right? So this is so wrong that we have those personal firewalls or antivirus products which use those rootkit-like techniques. So we should really get rid of them. And by the way, this brute force attack, which I mentioned, which could be used to blue screen machine once it's blue pilled. So one of the advantages of having blue pill level 2 would be that it shouldn't be possible to have similar attack against blue pill level 2. But still, we think that it might be possible to come up with another brute force attack, which would be possible to crash the system, which is blue pill level 2, when some very special conditions when they will be met, like user removing SATA disk driver in some in some specific moment during some specific test. So after I posted my blog entry about Bluepill, lots of people started insinuating that I'm paid by Intel just because I developed it for AMD 64. I developed it for AMD 64 just because this was part of more general research than on Vista 64, and the natural choice of processor for Vista 64 was AMD 64. So because I was doing some other research on AMD 64, naturally I investigated also this SVM technology. As we have seen today, it was the first time I've seen Dino's presentation. We can do the very similar thing on VTX as I did with Bluepill. So I wrote, it seems possible, but we now know that it is possible to port Bluepill to VTX. Still, it seems that Pacifica technology will already offers a little bit more functionality, which at the moment could be used to come up with a protection against Bluepill, not detection by protection, and Intel doesn't have it. And it seems that some other technologies, with this time can be used for creating Bluepill level 2, will be available faster on SVM rather than on VTX, like 1 year earlier. Bluepill prevention. Well, we just heard that you can disable hardware virtualization on Intel processors in BIOS. In my computer, which has SVM, I cannot disable in BIOS. There is no option in BIOS for disabling SVM extension on my AMD machine. But I heard that they are going to release some updates for BIOSes to make it possible. But still, it's a little bit crazy idea to recommend it as a protection, because we had all those people working for many years to come up with this virtualization technology just for us to disable it in BIOS, right? So it doesn't make much sense. And of course, virtualization technology is very cool. It should allow for doing very good things, right? Not only for creating malware. Another idea is hypervisor built into operating system. So we can imagine Microsoft providing their own thin hypervisor, which would just be used to prevent other hypervisors from installing. There is no such hypervisor on Vista, and I heard somewhere that Microsoft is working on its own hypervisor, but it's like a 3 years time frame. But still, the technology we have seems to make it possible for creating such hypervisor. But then the question is, again, we have this virtualization technology, so it doesn't make much sense to just disable it. So the question is, what would be the policy to allow third-party vendors to load their own hypervisor, like VMware, for example? The question?
Could you have it so that it only detects when a copy of the current settings are duplicated to the VMCB, so that it knows that this is so that it only detects Intel-like activities allow?
The question was if it's possible to detect it when I try to clone this virtual machine. In my opinion, this would be too difficult, because you have to have some kind of behavioral arbiter which would observe what actually. No, that would be too hard, because you would have to. Because this is a hardware instruction, right? You just run VM run instruction. So this would introduce a big impact on VM run. But who would compare it? Who should compare it? Who? Okay. So yeah, but I can create VMCB in many different ways. Well, not so many, but probably many different ways, more than one way, right? This is not something which could be detected by signature scanning. So there might be we would have to have some non-trivial logic in this hypervisor to judge whether what we are trying to do is to cloning the virtual machine, or we are just VMware trying to run a standard virtual machine, whatever. So the question is, and of course I don't know the answer, what would be the policy for allowing other people to insert their own hypervisors? And I also know that some, not only virtual machine vendors would be interested in inserting those hypervisors, but also providers of antivirus technology would like to sit in a hypervisor, right? To be able to see the system from a non-compromised, from a non-compromised point of view. We can also think about modifying SVM technology in such a way that it wouldn't be possible to move the operating system on the fly into the virtual machine. So for example, we could forbid or we could require that every created VM should start running in real mode, not protected mode. But again, that would be some loss of functionality, and it wouldn't solve the problem of permanent, so classic, like Subvert-like based malware. Another solution which I've thought of is to introduce another instruction, like let's say SVM check, but the point is that it should take some kind of unique password, which is unique for a specific machine, and which returns if you're inside VM or outside VM. Sorry. In my opinion, it's necessary to have this password, because if we didn't have it, then we don't have a full virtualization, right? Because then we can write a generic program which behaves differently inside VM and outside VM. So, but if we had this like 64-bit password, which we get like on a special certificate on with a processor. So we buy a processor, we get a certificate and a password on it, and we enter this password into our antivirus program during installation. That should allow for detection. But on the other hand, within the next few years, like 3-5 years, we should expect that everything will be run inside VM, right? So this would be a good solution for now, where we know that like Vista or some other standard desktop OS, they don't run inside VM, so that would be useful for detecting blue pill. But in a longer perspective, it's, everything would be run in a VM, so this wouldn't be useful too much. Okay, so we've seen today that arbitrary code can be injected into Vista 64, of course, provided that attacker first got administrative rights. And we've also seen that this could be abused, for example, to create blue pill-based malware, which is based on hardware virtualization, which is available on AMD64 processors. We've seen that blue pill installs on the fly, so it doesn't introduce any modifications into BIOS nor hard disk. And well, blue pill is just a general hijacking technique that can be used in many different ways. Delusion was just one example, very simple example, how to use it to create network-based backdoor. Blue pill should be, or I believe that blue pill is undetectable in any practical way, and I stress the practical because, as I said, I'm aware of a few theoretical attacks, which I don't think could be used on a massive scale or in a corporate environment. Blocking blue pill-based attacks on software level might prevent other independent software vendors from providing their own VMMs, which might not be that good. Changes in hardware might allow for easy blue pill detection today. Yeah. These are references. The following people contributed to this presentation directly and indirectly. Okay, and I think, yeah, that's all. Thank you very much.